All right, welcome. Let's get started. The grader has returned the first assignment in record time. I think that's going to work out great this semester. Now, obviously, I'm not the one grading the assignments, but I want you to get full credit for the work that you've done. And so if you have any concerns with how your assignment has been graded, please come see me during my office hours, and that's definitely something I'm willing to take a look at. I don't want you to feel like you've been unfairly penalized, so let me know if you think that you have. Your next assignment is due on Tuesday at the beginning of class, and I'm going to cover two of the problems that are on that assignment as some key ideas. And then a week from today we'll have our first quiz. I'd encourage you to show up on time for that because you're going to need all the time that you've got for the quiz. So don't be late. Yeah? No. Yeah, I'll provide any equations that you need for the quiz. Today we're going to be talking about vapor pressure and hydrostatics. And we're still in chapter 2 of the textbook. Hopefully you're following along with the concepts that we're covering because the book does a nice job with some supplementary diagrams and explanations. All right, let me dim the light so you can get a good look at what's going on here. Anybody have coffee this morning? No, water doesn't count as coffee. All right. Boy, a lot of late arrivals. You know, class starts at 11, and it's very disruptive for people to be constantly coming in and clacking the door shut. So either show up on time or just watch the video. I'd really rather that people not come in after we begin the lecture. Okay, so what we're looking at is a coffee pot that's boiling. And at sea level, water boils at 100 degrees Celsius, and that's a function of the fluid properties. There's something about water that's different from other fluids. You know, different fluids have different boiling points. And at Mount Everest, water boils at a different temperature. And it's not because water goes through some sort of a chemical transformation at higher elevations. It's still the same fluid, but it's that the vapor pressure, as we're going to be talking about today, varies as a function of temperature, and at different elevations there's a different atmospheric pressure. And so there's this sort of nexus of vapor pressure, temperature, and the pressure of the surrounding atmosphere. So that's what we're going to be talking about today. So this definition of vapor pressure, most simply, you can think of it as when a liquid will boil. It's the pressure at which a liquid will boil. So it has a temperature dependency that the vapor pressure of a fluid goes up when the temperature increases. And one way that I like to think about it is as a basin of water. There's the atmosphere pushing down on the top of that surface of water. And at sea level, the pressure of the atmosphere is 101,325 pascals. Now, the water, some of the water molecules there have enough kinetic energy to be escaping, and that's what causes evaporation. And so there's something that we can think of as a pressure that the water is exerting in opposition to the atmospheric pressure. And this is the pressure of the vapor. Welcome. Glad you could join us. All right. Oh, okay. Awesome. So the vapor pressure varies as a function of temperature. And what we have is when the temperature is 100 degrees Celsius, then the vapor pressure at 100 degrees Celsius is 101,325 pascals. And that's why we see the boiling, is because the two things are equal as the temperature increases. So here's a table of water's vapor pressure at a variety of temperatures. And what you may remember back from chemistry is, you know, there's lots of different ways to measure pressure. There's PSI, pascals, kilopascals. Well, one of the ways of measuring pressure is in terms of millimeters of mercury. And you probably remember that 760 millimeters of mercury is equal to atmospheric pressure. And so that just corresponds to 100 degrees Celsius. And it's not that it just happens to correspond. That's by design that the scale in Celsius was set so that at 0 is when water freezes and 100 is when water boils. And so vapor pressure of water at 100 is 760 millimeters of mercury. So here's just a graphical way of looking at it. And this illustrates that it's a nonlinear relationship. So this is showing that at first the vapor pressure is increasing very slowly, but then it increases quite a lot. And so you can get an idea of, for instance, how quickly water will evaporate, because vapor pressure kind of gives you an idea of the speed of evaporation. And during the wintertime months, when the vapor pressure of colder water is going to be very low, then there's going to be a big decrease in the amount of evaporation speed compared to when temperatures are high. Water can also boil for another reason besides just increasing the temperature of the water. You can also boil water by decreasing the pressure above the water. So what we said before was that when the two pressures are equal, when the vapor pressure is equal to the atmospheric pressure, then we'll begin to see boiling. But if you reduce the atmospheric pressure that's above the water surface, then that will mean that there's enough kinetic energy in the water molecules under the surface that they can begin escaping from that interface. So let's take a look at a short video that shows that process of getting water to boil at room temperature. Okay, so here somebody has a vacuum pump and it's connected to the top of a mason jar and the water is boiling. It doesn't make the water hot. In fact, the water begins to get colder, which is sort of contrary to what you might expect. But the reason why it's boiling is that there's enough kinetic energy in the water molecules to go from the liquid phase to the vapor phase. It's not like this water is turning into air. It's still H2O as it goes through the phase transformation. It's just that it goes from liquid H2O to vapor H2O. Now earlier I said that this is actually getting colder, that there are some videos online where it actually turns into ice with a powerful enough vacuum and given enough time. So any idea why the temperature is decreasing of the water? Well, it's the pressure change that causes it to boil. So indirectly that's true that it's the pressure change, but it's actually something else. Okay, that may be part of it. You may also remember from chemistry that when you were talking about phase changes that it requires heat, for example, to go from ice at 0 degrees Celsius to water at 0 degrees Celsius. So even if the temperature isn't changing, the phase change itself requires energy. And so to go from 0 ice to 0 water takes heat. And so what we were just watching is another phase change. We were watching it go from water to gas. And even when it's going through that phase change, energy is required, and it gets the heat that it needs for the phase change from the water. And so the temperature of the water is decreasing, and if it goes on long enough, then the water will freeze. Unfortunately, that video that I've got, which is this link here, I just checked today and it's not available anymore. I think maybe the owner of it has taken that video down. But anyways, trust me, it's basically the same thing. The water's boiling until suddenly it's just a block of ice inside of the vacuum bell. The vapor pressure, you can look up in the back of your book. There's in table A5, not only the density, specific weight, the general fluid properties that we've used a lot, but here is the vapor pressure in terms of newtons per meter squared. So this is the absolute vapor pressure of water at a variety of different temperatures. And just as we'd expect, 101.3 kilopascals is where the water begins to boil. That's when atmospheric pressure is equal to the vapor pressure of the water. So it's more than just a curiosity, though. Actually, this idea of vapor pressure is pretty significant when you end up doing hydraulic design. And here's a picture of what used to be a big dam in Russia. This is before, and there was a big hydroelectric station there that was generating a lot of electricity in that region, which is known for the production of aluminum. They've got a very electricity-dominant industrial base that sort of was in bad trouble for a few years as there was a series of explosions at the dam that initially they wondered maybe it was terrorism or something, but upon further investigation they found out that the water was cavitating as it passed through the dam. And what that is the pressure was decreasing as water flowed through pipes inside of the dam to the point that it was actually the water was turning into water vapor because of a low pressure section inside of the pipes, and then the water bubbles, when they go back to a high pressure location, they'll collapse very quickly. That's the process of cavitation, and it sends small shock waves through the pipe, and any one little water vapor bubble that collapses isn't going to cause this. But over the long term, the structural integrity of a pipe can be eroded as the tiny little water vapor collapses, chips away at a pipe, and what happened was that what you're looking at here on the generator's floor, there is it's the opposite of a pump. It's an impeller that's put into the flow that's spinning around, and it spins the generator, which turns that physical motion into electrical motion. And the cavitation bubbles on the impeller that was spinning made it sort of go out of an alignment, and it got wobbling and even more stable until it just completely destroyed the entire electrical production side of the facility. So kind of an interesting application that we'll come back to multiple times, not only in this semester but also next semester when we're talking about what to look out for in hydraulic design. Okay, so for the rest of today's lecture we're going to start focusing on pressure intensity. And the big thing in Chapter 2 that you can expect to see, for instance, on the FE exam are calculations related to hydrostatics. It's a huge part of every fluid mechanics course, and so understanding pressure and what causes it will allow you to solve some of those problems. Pressure is measured in units of force per area, so newtons per meter squared, which is the same as Pascal. Now, pressure is independent of direction. It's just a scalar. And so if you're submerged down in the ocean and you try turning your head side to side, that's not going to decrease the pressure that you face. If you've ever been swimming in a pool, you'll know you can maybe equalize your ears by trying to blow air, plugging your nose and blowing air so that the pressure increases on the inside of your eardrums. But if you go really deep into the ocean, just turning your head side to side isn't going to allow you to escape the effects of pressure. So here is a representation of two different reservoirs. One reservoir is much larger than the other. It looks like they have the same depth. And so let me ask you a thought question. Which of these two reservoirs is going to have a higher pressure at the bottom of the reservoir? They're equal. Some people say the one on the right. It's the one on the left just for balance, I guess. Pressure only depends on depth. And so it doesn't matter if you have a very narrow column of water that you're going down through or a very wide column of water. The water that is to the side of you isn't what's causing the pressure on your ears when you swim. It's only the water above you that's causing the pressure in your ears. And so that's why they can test submarines in Idaho, for example. And there is a submarine test facility in Idaho, believe it or not, in a very deep lake. They don't need to necessarily test submarines in the ocean, where the ocean is wide and deep. All they have to do is find someplace that's deep, and they can simulate the pressures that they need to see to study submarines. Okay, so here it is, the big equation. This is the hydrostatic equation, and what it says is that the ratio between the change in pressure and the change in elevation is equal to the unit weight of water, specifically the negative unit weight of water. Now, what this means, the negative sign there, is that as you go up through water, the pressure decreases. And that's what you'd expect. I think that's intuitive, that as you go downward through water, the pressure is getting larger. As you go upward through water, the pressure is decreasing. We measure the elevation relative to any location. It doesn't matter if it's at the bottom of the tank or at the top or in the middle or maybe at a point of interest, so long as every time we refer to a change in elevation we use that same datum, then that's fine. The location doesn't matter so much as that we're consistent as we measure the location. Now this unit weight, if we're talking about water, it's 9810 newtons per meter cubed for just sort of the default standard conditions. It'll be less than that for oils, more than that for things like mercury. But it tells you the rate at which pressure is increasing. So every meter that you go down, if we have gamma is 9810 newtons per meter cubed, what that means is that if you go down in depth 1 meter, that the pressure increases by 9810 newtons per meter squared. So you multiply that by a depth, which is measured in meters, and then you'll get a change in pressure. That's one way that we can abbreviate and apply the hydrostatic equation. So from a unit standpoint, if you look at the units of pressure, it will be newtons per meter squared, and you're dividing that by meters, which is a change in elevation, and then that on the left-hand side, the units are consistent with what we have on the right-hand side, which is newtons per meter cubed for the unit weight of water. We usually assume that because fluids like liquids are relatively incompressible, we'll assume a constant density and a constant specific weight through the depth of a liquid. And so we can integrate the hydrostatic equation to get an expression we're going to call the piezometric pressure. And what piezometric pressure does is it keeps track of both pressure and location as you move around inside of a tank. And so referring back to this drawing of a container of water, if we have a couple of locations that we're interested in, here's location 1, here's location 2, let's say that we're measuring the elevation of those locations above a datum. So the bottom of the tank is where we're going to measure how high up they are. Where would you expect there be greater pressure? At 1 or at 2? 2. At 2, because it's deeper down into the tank. So you're right. What the piezometric pressure, though, says is let's not keep track of just the pressure. Let's also look at how high above the z datum they are. And so between location 1 and location 2, the p sub z of location 1 would equal the p sub z of location 2, because although the pressure is bigger at location 2, it has less z. So the second term in the piezometric pressure is this gamma times z parameter. And so if you have a hydrostatic situation, which is water that's not moving, water inside of a tank, you can move around any place in that tank and have constant piezometric pressure. It's only when liquids begin to flow, when you have non-hydrostatic conditions, that the piezometric pressure would be different inside a continuously connecting body of a fluid. But this is just the first time you'll see this definition of piezometric pressure. We'll come back to it again through the semester, but what allows us to do is express it a different way. If we divide each of these terms by gamma, another way of expressing the same idea is with piezometric head. And so whether we're talking about piezometric pressure or piezometric head, as we go anywhere inside of a tank between locations, it's constant, meaning that you have an exchange between elevation and pressure. As you go down in the fluid from 1 to 2, because location 1 is above location 2, so if you go down through the fluid you're increasing pressure, but you're decreasing Z, and in a way it's an exchange. You're having the increase in pressure because of the delta Z times the unit weight, gamma, of the fluid. So we can use this hydrostatic equation between 2 points in a liquid where the liquid isn't moving. That's the static component of the hydrostatic equation, is that what we're talking about here, it can be liquids in different locations even. It could be a tank that's connected to another tank by a pipe, and if we had the tank that's high enough so that they're connected and the water isn't flowing between them, you can use the hydrostatic equation between only points where the water isn't flowing. So why don't you use this example to get a little first experience using the hydrostatic equation. We have a tank that has water in it, and we're measuring these elevations relative to a datum. You'll notice that here a gauge pressure is listed for location 1, and it's asking for the gauge pressure at location 2. And so we know the initial pressure here at 1, we don't know the pressure at 2, but we've got the elevation for both. And then it's also asking in part B to find the absolute pressure at 2. And remember that the difference between absolute pressure and gauge pressure is one of them uses the vacuum as the starting point for measuring pressure, and the other says let's have atmospheric pressure be equal to 0. So converting between the two of them, absolute and gauge pressure, is just a matter of adding whatever the atmospheric pressure is. And here we're going to assume that the typical atmospheric pressure is 101,325 pascals. All right. So calculate those two things. A couple of suggestions as you're working. I'll reiterate my suggestion that you should always write the units as you're doing these calculations, because it's going to save you a mistake either on a homework assignment or on an exam or a quiz. So if you had 66 and didn't write kilonewtons, because maybe you're wanting to work the problem in kilonewtons rather than newtons, and then divided by 9810, then all of a sudden you'd have a discontinuity in the units there. But if you had written 66 kilonewtons and then 9810 newtons per meter cubed, then you'd see I need to be consistent both ways. So including the units every time you set up every step, then you'll avoid those sorts of mistakes. So here the pressure is going to be increasing. We can, even before we start crunching the numbers, just look at the picture and try and say logically, what do I expect the pressure at 2 to be? Well, I think it's going to be higher than 66,000 because it's deeper down into the tank. So even before you start putting in your calculator, you can start thinking in terms of reasonableness. And so we expect it to be higher than the starting pressure was at location 1. And when we do the calculations, we find, in fact, that that is true. It's higher than the starting pressure at 1 was. And so here we have the gauge pressure. And to convert between gauge and absolute, we simply just add the effects of the atmospheric pressure as well. So you take the gauge pressure, add atmospheric, and then that gives you absolute pressure. And then I included a sketch. Even though we were just looking at a sketch, I really think it's a good idea just to get in the habit of putting these sketches onto your examples and your homework problems. There's just something about doing it with your own hand that makes the problem more real and easier to envision. So, any questions on this example, the hydrostatic equation? I mean, go ahead.
Why did you choose that specific way?
Why? Yeah, good question. Thank you for asking that. It's because it just said that this is water, but it didn't provide any temperature. If it had said water at 20 degrees Celsius, then I would have said 9790. But water with no temperature specified, I think the default for us to use is just going to be 9810 newtons per meter cubed. And that would be the unit weight at water at a little bit cooler than room temperature. Most of the water that flows through pipe networks is at about 55 Fahrenheit, in that range, because ground temperatures are cooler than room temperatures. And so I think maybe 9810 would correspond to the unit weight of water that you'd see going through a municipal pipe network. Closer anyway. Thank you for asking that. Is there any other questions related to this example? Yeah. Good question. So here, I guess maybe just it's like a round-off thing. It's where I say, let's see, what was the problem given as? Okay, newtons per meter squared. I didn't have to convert to kilopascals, but what was the point? No point. You didn't have to. I didn't expect you to. I did it just because, I don't know, maybe it's fewer pen strokes than writing all that out again. Yeah. No reason besides that. Other questions? Yeah, and so why didn't I do it here, right? Why wasn't this 246? Maybe it should have been. All right. All right. So you know the hydrostatic equation now. If you look at the course description, that's a big part of the course description, is knowing and applying the hydrostatic equation. So that doesn't mean we're done for the semester. That just means you've got a really important tool that you can apply to solving lots of kinds of problems. And so you can get an early start on the homework. Knowing the hydrostatic equation, you can make it pretty far on that next assignment. There's an abbreviated version of the hydrostatic equation that says, instead of always finding the absolute pressure at a location, why not just think in relative terms? Why not think about a change in pressure between points? And so that's what this delta P formula is all about. It says that if we say that there's some change in Z, a change in elevation, so here in this problem, the change in Z that we had was 34 minus 26. So let's call that difference in elevation delta H. And then if we multiply that delta H by the unit weight, that tells us the change in pressure between 2 points. So Challenger Deep is at the bottom of the Mariana Trench in the Pacific Ocean, and the depth there is 10,911 meters. Since that's in the ocean, the unit weight that we should use is that of seawater. It has a higher unit weight because of the salts that are dissolved in seawater compared to freshwater. So from the surface to the bottom, what's the change in pressure for Challenger Deep? Do those calculations. It shouldn't take too long. Okay, so from the surface to the bottom is delta H of 10,911. The unit weight of seawater is given in the problem statement. That's something that you could have looked up in the appendix from the fluid properties table. But the abbreviated hydrostatic equation is just a change in pressure as a function of the change in depth and the unit weight. So if you multiply those two together, you get 110 million newtons per meter squared. So that's 110 megapascals. Anybody remember what the typical water pressure is in a pipe network through the city? It's about 500 kilopascals. So this pressure is way, way, way beyond that. You know, this is like 200 times as much pressure as comes out of the pipes in your house. So that's a lot of pressure. That delta P that we're talking about is a change in pressure, and we we don't know if that's not really an absolute or a gauge pressure. That's just a change in pressure. So if we want to know what is the actual pressure at that location, if we're describing it in gauge, we assumed that at the surface of the water the pressure was 0, because we were saying let's neglect the effects of atmospheric pressure and just say we're measuring increases above and beyond the atmospheric pressure. But if we want to add the effect of atmospheric pressure on top of that, then the absolute is just 0.1 megapascals more than the gauge pressure was. Okay. So any questions about the abbreviated hydrostatic equation? All right. Well, let's cover 2 points of key ideas. So everybody here has had their lab now, and how many people saw the needle float on top of the water? The needle floated, right? Now when it did, let me blank this out because for now we're not going to look at that picture. So here's water. Boy, these markers really leave a lot to be desired. Here is the needle. Now, it's tempting to draw the needle as a line, but really it has thickness, and so let's not consider it as a line. If it's floating in the water, it's bending the water surface not just in one place, but effectively in two. It's bending the water surface here on this side, and on that side it's bending the water surface. You know, it's also bending it at the ends, but the length of the ends is so small relative to the length of the needle that we kind of ignore the end length. And so I referred to this before when we were talking about how the bug's leg deflects the water surface, that the same thing is true of the needle. If you have a needle that's resting on top of water, then it bends the water surface in two locations. Okay, so that is for a straight object that's bending the water surface. In one of your problems, what you're going to be working with is something that has the shape of a ring. And this is a way of characterizing the viscosity of water. When you don't, I'm sorry, not the viscosity, the surface tension. This is a device that's used to identify how much surface tension a liquid has. And so you can see in this picture it's being pulled up out of the water, and it's kind of the opposite of it resting on top of the water. Here, the water continues to cling onto the surface of this ring, and so that some additional force is required to lift it out of the water compared to just the weight of the ring. We're looking at a cross-sectional view here. Let me give you a top view of what this ring looks like. So this is a ring that goes all the way around, and this cross-sectional view is just cutting the ring here so that we're looking at the thickness of it. So in the problem statement, it's telling you the inner diameter of the ring. It's telling you the outer diameter of the ring. So back to this idea of the needle floating in the water. Where is this ring bending the water surface and interacting with surface tension? Around the circumference. One circumference or two? Two, right, yes. So it is the inner circumference that's bending the water, and it's also the outer circumference that's bending the water. And that's why in this problem they had to specify both of those diameters. It's not about how thick is the ring, not directly. What it's really more about is, remember in the equation for surface tension, you want to find the force of that surface tension. It's a function of the surface tension constant, which in this problem is the unknown. We don't know what is the surface tension constant for this fluid. But we do know indirectly what force is required to overcome the surface tension force. And then the lengths are what we come from, what we get from the dimensioning that's provided. So circumference is pi d, right? That's how you find the circumference. And so you've got the total length is going to be the circumference of the inner ring and the circumference of the outer ring. So that's the total L parameter that you're going to put into this equation here, is the total length that is being bent by whatever this device is, this ring that's being pulled up out of the liquid. So is everybody with me so far when we're talking about the length? All right, so here it's saying we don't know sigma. We don't know what is the surface tension constant for this liquid. That's what this whole setup is meant to characterize. But we do know that they're having to lift it out of the water with a force equivalent of 16 grams. This word equivalent, what does that mean? Equivalent. Multiplied by gravity. Yeah, grams isn't a unit of force. Grams is a unit of mass. So in the problem statement it says that it's being lifted up with a force equivalent of 16 grams. And so you need to convert that to an actual force by going from grams to newtons, by divide by 1,000 to get kilograms, then you multiply by 9810, which is G, and then that'll give you the force that they're lifting up with. The ring mass is given, so what does that enable you to calculate? Well, that's not the force of the tension, that's the weight of the object that's acting downward. Because really, what we're going to have to do for this object is a force balance. And there are three forces that come into play. If I do this little cross-sectional drawing here, it's being lifted up. Okay, so there's the force that they're pulling with, and then there's what we say the weight is acting downward in both of these locations. It's not that there's two weights. I mean, we're looking at a cross-sectional view. There's a single weight force that's acting downward. What's the third force? Yeah, it's the water, or this isn't water, whatever this liquid is clinging on to it. And so is that an arrow up or an arrow down? It's down. It's resisting. Because what they say is that the ring only has a mass of 10 grams. And so if there was no surface tension happening, then F would be 10 grams. So there's some additional force that's required to lift it up out of the liquid. That additional 6 grams is due to the surface tension. So that's essentially 6 grams is the difference in the forces. So there's force due to surface tension acting downward. So if we're going to say what are the sum of the forces in the vertical direction, that's this force that's up minus the weight of the object minus the surface tension force is equal to 0. Okay, so what do we know? We're given F directly after we multiply by G. Okay, we know the weight of it by multiplying by G. So from the force balance you can find the surface tension force, and so here we know that. From the diameters you can get the length, and that enables us to calculate the only remaining unknown, which is the sigma, the surface tension constant for whatever this liquid is. Okay, so everybody feel comfortable how to begin on this problem? Any questions before we move on to the other one?
Does something with the square cross-sectional area act in a different way from the circular cross-sectional area?
Good question. So you're saying what if instead of a ring, what if it was a rectangle or a square of some sort?
Not necessarily the shape of the item, but its cross-section.
Oh, okay. I see what you're saying. Yeah, so instead of bending the water like this, it would be like that. I don't know. I'm just suspecting here that these edges might be prone to piercing through the membrane more easily than a curved cross-section, but I guess the only way we'd know for sure is to go into the lab and give it a try. So that's just speculation. My guess is probably it wouldn't work as well. Like you wouldn't be able to rest it on the water as easily. You know, when we were talking about the bug's legs, they're flat rather than acting downward. But good question. Okay, here's the other one I wanted to talk about. Problem 272. This picture is not from the problem. This is just a picture I found online to illustrate the point. Okay, in this problem they're trying to find out what happens as a function of elevation. And so here's what we know about sea level. Sea level has an elevation of 0 meters. The atmospheric pressure at sea level is 101 kilonewtons per meter squared. and water at sea level boils at 100 degrees Celsius. That's vapor pressure. Remember that water boils when atmospheric pressure equals the water vapor pressure for a given temperature. So the water vapor pressure is 100 associated with boiling at atmospheric. Okay? Now consider higher up, at an elevation of 3,000 meters. In the problem statement, it's telling us that at 3,000 meters, the pressure is 69 kilonewtons. And so they want to know essentially what temperature is the water going to boil at that high elevation. If any of you are into baking, and I assume everybody here is into baking, right? If you've ever looked on the back of a cake, you may notice that it has what are called high altitude instructions, where actually what they tell you to add, the number of eggs, the amount of oil, how much water, it's slightly different for people who live at a high altitude. And when I grew up, I lived in the mountains, and so we actually followed the high altitude instructions for making cakes and stuff. And I think what it was is you added less water in the high altitude. No, it must have been more water because things boil more easily, so I'm guessing in any case it was different high altitude instructions. I don't remember whether it was more water or less water. It's been a long time. But this problem is saying if you're given this relationship of delta P and delta T, so it says that the relationship between change in pressure and change in boiling temperature is for every 3.1 reduction in kilonewtons per meter squared. So as the pressure goes down, then the change in boiling temperature is 1 degree Celsius. And so earlier in this lecture, I told you that at Mount Everest, at the top of Mount Everest, I think it was the boiling temperature of water was 69 or something, 69 Celsius. So this isn't going to be quite as depressed as that. That's the highest point on Earth. So somewhere between 69 and 100 is what you should expect to see for this problem. Auto recovery. All right. So the reason why I wanted to give you some hints on this one is it seemed like the essence of the problem was kind of hidden in the language for that one. I wanted to show you a picture of it and show you what this gradient was all about. It was about the change in pressure relative to the change in temperature. So there's an inverse relationship there as the water boiling at a lower temperature as the elevation goes up. Okay, so that assignment, including those two problems, is going to be due at the beginning of class on Tuesday. We're going to continue talking about hydrostatic forces and the effect of how pressure influences gates, both curved gates and flat gates. And so I'd encourage you to keep up in the textbook. It's really a great supplementary resource that can help you understand the concepts. But let me know if you have any questions on homework 2B. I'll take the key home with me over the weekend, and so if you have any questions by email, I'll do my best to respond. Just let me know. Have a great day. I'll see you on Tuesday. And if you didn't get your assignment yet, it's here at the front on the table.